everyone. My name is Annika Smith, and today I will be starting this new Stat 231 video series, if you recall my CO250 video series. And I want to go through this example that I made up about calculating a confidence interval for a binomial distribution. So I don't want this video to be too long. I wanted to hop right into it. Okay, let's go. So Annika picked up a lucky nickel, and she's curious as to whether it's a fair coin or not. So I'm going to run this experiment where I flip the coin 10 times and write down how many heads I get. I got 8 heads. Okay, that seems like a lot of heads, but we'll just do some calculations there. We're going to assume that this is a binomial distribution, which makes sense given our context, and assume that my flips are independent. So we see that we have 10 trials, but we're not sure what theta is, aka we're defining theta as the probability of observing a head being a success in this binomial experiment. So we're asked to compute a 95% equal-tailed asymptotic confidence interval for theta. And then we want to interpret the result and apply it to my question, aka, is the coin fair? So first I want to mention, I'm not exactly sure if this is how this would be worded in our class. 95% equal-tailed confidence interval, you should understand. This asymptotic part is just in reference to the fact that I want to use the asymptotic pivotal quantity. And what does that mean? Well, basically, from what I understand, there's exact pivotal quantities, which are these like kind of quantities that we use that are based on the distribution that we're originally using. So, say a pivotal quantity based on the binomial distribution in this case. Whereas the asymptotic ones are, we apply the central limit theorem to approximate our distribution as the Gaussian distribution instead. That's why we call it asymptotic or approximate. So we're going to use the asymptotic one here. And this is something you should have on your cheat sheet. What exactly is the asymptotic pivotal quantity, specifically for the binomial? And it looks like this. So I'll write it out here. We got our estimator, theta tilde, minus theta, the true parameter, divided by this funky thing of theta tilde 1 minus theta tilde, all that divided by n. This is all in the square root here to make that a little bit bigger. So this pivotal quantity here, we went through this in class, and it is modeled by the Gaussian distribution with a mean of 0 and a standard deviation of 1. And there's a lot of theory behind this that we covered in class that I don't have the time or, frankly, the ability to get into too much. So I'm just going to take this as given that this is my pivotal quantity, and then I'm going to show you how I compute the confidence interval based on this pivotal quantity. So, what is a confidence interval? Well, essentially, we want to have this interval where we're 95% confident that the true parameter theta will lie in there. So we set up this probability. So we say that the probability of, and we have an equal-tailed one. So I make equal tails. I have a negative A and an A. And in the middle here, I have my pivotal quantity. And we want this thing equal to 0.95 or 95%. So once I have that, I can start figuring out some of the things here. Like what we're going to do is I put this pivotal quantity in here. I need to solve for A, which we can use using the Gaussian distribution. And then I want to rearrange just to have theta on its own, which makes it a lot easier to actually see what the probability is and how it all works out, what my actual interval is. And then from there, we can do our analysis. So I am going to start by figuring out what A is, because I can do that right now. Because I know that this whole thing is based on the Gaussian distribution, put that right here. And if I want P of negative A less than or equal to this thing, which is Gaussian, less than or equal to A, to be equal to 0.95, that's kind of like saying P of Z less than or equal to A is equal to something. But I say that because notice how we have this part over here, whereas this part I've kind of just neglected that and I just have less than or equal to A. Well, if you'll recall, the Gaussian distribution looks something like this, and we're centered at a mean of 0, and we want to figure out this part here with the both sides. going to be negative A, and we want this area in the middle to be 95%. So how can we figure this out if we are only measuring like the entire lower tail? So we're like measuring all of this part. Well, in order to do that, we know that the area under curve is going to add to 1 or 100% of the probability. So if we have a 95 here, that means that the lower and upper tails must add to 5% to get up to 100. And then because the Gaussian distribution is symmetrical, we know that there's going to be equal area on the lower tail and the upper tail. So I just split that in half. I know that this is going to be 0.025. This one's also going to be 0.025. So now that I'm measuring this without some sort of lower bound down here, I know that it's going to, this value over here is going to have to be 95% plus my 2.5% for the lower tail. So that's where I get this value from, like that. And now we can go about figuring this out. So there's two ways I believe that we do this, like say in a test. And that would be one is to look at the R code. So we might be given a snippet of R code to figure out, okay, which one is the A value I'm looking for. Or we could be given a table or snippets of the table of Gaussian distribution quantities. So I'll walk you through what both of those will look like. So I have some R code here. And you can see up here, it's going to be Q norm. So this is going to be the probability I'm looking for, the 97.5%. Lower tail equals true is kind of what I was talking about over here, where we're calculating this part of the distribution. If it was lower tail equals false, it would actually be the upper tail, so it would look at this part instead. But I don't want that. I just want the lower tail, so lower tail equals true is good. And then it automatically assumes if you don't put it in that the mean is 0, standard deviation is 1. You could change that, but we don't need to for this example. So I can just compute this, and I get that my A value down at the bottom there is 1.959 or 1.96. We'll round that to. So you might get a snippet of code and have to be able to derive that yourself. So I'm going to put that A equals 1.96, and then I'll show you the other method as well. So we could be given a table that looks kind of like this, and it gives us the probabilities for the normal distribution, which with 0 and 1 is the same as the Gaussian distribution. The only difference being the second parameter there. In the normal distribution, it represents the variance. Gaussian, it represents the standard deviation, but it doesn't matter here because it's just 1 either way. So we are going to look in here. We might be given something like this, where I would find my 97.5%. But because this chart doesn't include the 97.5, I'm going to show you how it looks like in this chart. And I remember doing something similar to this in high school, where it's like, okay, we're given, like the A values are going to be my cross-reference on the column and the rows here. And all the values in the middle are the probabilities. So I have to kind of do this like reverse lookup thing. So I want to look for a 97.5 in here and then see what it references. So I'm going to look around here. Okay, got a 97.3, probably a little bit bigger than that. Okay, right here, 97.5 or 975. So I found that value. It's exact. That's the closest I can get to that. Right on. And I see that it corresponds to a value of 1.96. So that would be how I get the A value from a chart like this. So I got A is 1.96. Cool. We can plug that in. And now I have to rearrange my probability to just have theta in the middle. And now this is just a bunch of kind of work that we're used to doing with stat 230. So I have negative 1.96 less than or equal to theta tilde minus theta over this standard deviation over root n business. Recall that the standard deviation for the binomial distribution looks kind of like this if you recall from stat 230. If you don't, just write on your cheat sheet, no worries. And the first thing I want to do is multiply out the denominator so I can start just having theta on its own in the middle. So when I do that, theta tilde, 1 minus theta tilde over n. And I don't blame you if you want to fast forward this part because you might be way more of an expert on this than I am. So I do not. I encourage you to do that. So, okay. Then from here, I can just subtract my theta tilde. And then, uh-oh, this keeps happening to my pen. Alrighty. Okay, p of negative 1 point. Get rid of this little thing here. So this kind of process will be very similar for any asymptotic pivotal quantity, or frankly, any pivotal quantity that you're trying to convert into just um, like the confidence interval. But there are some variations, like, for example, the standard deviation for all the distributions is going to be slightly different. Like for here, you can see the binomial, it's this like part of the numerator here. For the Poisson, it would just be root theta. For exponential, or I always get confused between Poisson and exponential. One of them is root theta, one of them is just theta. So keep that in mind. Um, that'll definitely be something that goes on my cheat sheet. But from here, I don't like this negative theta here. I'm just going to multiply by 1 or negative 1 to get rid of it. So if I multiply everything by negative 1, I have to flip the signs here. But I don't really want it to be like greater than or equal to the signs, so I'm just going to use this kind of thing here. So like say I have A less than or equal to B less than or equal to C. I know that if I just write this, ooh, wait, I'm getting confused. Hold on. I'm going to write this in the way that I did it last time. So once I multiply everything by negative 1, I'm going to have something that looks like this. And then if I want to just write this as less than or equal to signs instead, I can just flip the A and the C like this. And you'll see that these are the exact same thing. So I'm just combining those two steps where I'm multiplying by negative 1 and I am flipping the signs like I showed here. And basically, like I'm doing all this work just kind of show you where this is coming from, and I hope this makes sense. But you don't really need to do all of this work in at the end of the day, because all of these asymptotic pivotal quantities will have this exact same form at the very end. So you can just kind of like plug and chug the formula there and not have to worry about doing all this rearranging and stuff. So now we got theta in the middle. And this is going to be my lower bound here, and this is going to be my upper bound. So I already got that A is 1.96 over here. And now I just need to figure out what theta tilde and what n is. So we'll talk about theta tilde. And theta tilde is basically my stand-in for theta hat, which is my maximum likelihood estimate for the binomial distribution that I'm given here. And if you're not too much of a fan of chapter 2, don't worry. I'm not going to do the whole like maximum likelihood estimate derivation here. I'm just going to use our result that theta hat is y over n. So what's y, what's n? Well, let's take a peek at our question. So I observed 8 heads, that's going to be our y, and 10 times, that's our n. So I'm just going to write this as 8 over 10. You can put that in lowest terms if you want. I'm just going to leave it like that. And then that just gives us n as well, because we know n is 10. So I can calculate both of those things. So our 95% confidence interval is going to be, oh, I think it's because I keep pressing some button on my pen. Sorry about that. Okay, so plug that into your calculator with the theta tilde is 8 over 10, n is 10, and I have that in R over here. So I'm just going to compute these guys here. So we got that the lower bound is 0.552 and the upper bound is 1.048. So I'll put those in, 0.552 and 1.04. So now our last part of the question is just to interpret the result and apply it to my question. So we have that our lower bound is 0.552. That's kind of like saying in our kind of 95% guess of where theta might lie, the true value of my probability of getting ahead on this coin, it's going to be between 55% and 105%. You might be thinking 105%, that's ridiculous. Like, I can't have a coin that's going to give me a 105% chance of flipping a head. That doesn't make sense. And you'd be right. And I honestly can't really explain the theory behind this because I'm not quite sure I understand it myself. But this is just kind of our kind of wide guess interval for where theta is going to lie. Obviously, theta is not going to be greater than 1. That just doesn't make sense. But we just have this equal tail confidence interval, and that's where they leave us. So, where you can kind of just think of this as 0.55 to 1 if you want, I guess. But the real analysis part comes in when we consider, okay, is my assumption that this is a fair coin a reasonable one or not? Well, if this is a fair coin, then we're expecting that theta, the probability of getting ahead, is going to be 0.5. But notice that this value is smaller than the lower bound of my interval. And this interval here means that we are 95% confident that the true value of theta, the probability of getting ahead, is in this interval. So if I'm 95% confident that theta is in this interval, and the theta for a fair coin is not in that interval, that means um, I'm not very confident that this is the real value of theta. In other words, we have evidence to suggest that this is not a fair coin. Now, I can't just throw up my hands and say, oh, this is definitely not a fair coin, like I got 8 out of 10 are heads. No, this coin cannot be fair. That's just not the case, because there's always some element of randomness in life, and maybe the next time I flip it, I get exactly 5 heads out of 10. Who knows? So we can't just 100% conclude, okay, yes, this is a fair coin, or no, it's not a fair coin just based on this, but we have evidence to suggest one way or another. And if I ran a bigger study with maybe 100 flips, then I'd have an even better indication of whether this is a fair coin or not. So that concludes my video on how to compute a equal-tailed confidence interval for theta with a binomial distribution based on the asymptotic pivotal quantity, which we use the CLT to approximate. And I hope to bring you more videos like this. I hope this doesn't take too much time, and I hope you enjoy watching. So thank you. And I'll go over to my little thing and press